Well, welcome everybody to today's webinar on flash drought, co-organized and co-hosted by NOAA's National Integrated Drought Information System, or NIDIS, and the National Weather Service. My name is Marina Skumanich, and I am a program specialist at NIDIS focused on the Soil and Moisture Network Initiative. I will be moderating this webinar along with my colleague Maggie Hurwitz, who is the Hydroclimate Services Lead for the National Weather Service. A brief background on NIDIS. NIDIS was created by Congress in 2006 with a mandate to help the nation prepare for, mitigate, and respond to the effects of drought. NIDIS does this through a series of activities, including the development of regional drought early warning systems, as shown on the map here, and through support to improve drought predictions and forecasting, effective drought planning and preparedness, and assessing the impacts of drought. All of NIDIS's work is done in collaboration with a wide range of partners at all levels. In addition, NIDIS hosts the U.S. Drought Portal at drought.gov, which contains a wealth of information on drought research and conditions, including information on flash drought. The National Weather Service provides a number of drought products and services, in addition to all the other work that they do. Resources such as the Climate Services Operations Document, fact sheets and webinar recordings are available on the NWS Climate Services website. NWS drought products include the monthly and seasonal U.S. drought outlooks, which are produced at the Climate Prediction Center, and drought information statements, which are produced by the local weather forecast offices in times of drought. Also, NWS and NOAA are important partners in the U.S. Drought Monitor. Today's webinar is the last of a three-part webinar series focused on flash drought. This series was organized to raise awareness of flash drought, share current status and future priorities for research, and highlight emerging tools for flash drought. We've intended this series to be useful to climate professionals and operational service providers, as well as to the public. The first two webinars focused on the state of the science of flash drought, and then a review of current understanding and future research priorities based on the NIDIS 2020 Flash Drought Virtual Workshop. Recordings of these presentations are available on a link on this slide, which we will all be posting into the chat box. This final webinar today will provide an overview of emerging tools for flash drought monitoring and prediction. As with previous webinars, this webinar is being recorded and a link to the recordings will be shared via email and available through weather.gov and drought.gov. A quick overview of our agenda today. We will first have two presentations by staff at the NOAA Climate Prediction Center, or CPC. Chen will present on experimental subseasonal tools to support flash drought monitoring and prediction at CPC, followed by Pugh, who will present on an upcoming CPC product, Week 2 Flash Drought Forecasts. After that, we will have a presentation by Trent with University of Illinois Urbana-Champaign, who will provide a survey of various other emerging flash drought tools. At the end of the presentations, we will have some time for Q&A. If you think of questions during the presentations, please go ahead and put them in the questions box, and we will get to them at the end of the presentations. We will now tune to our first presentation, which is a pre-recorded presentation by Chen of NOAA's Climate Prediction Center. Gwen is here with us and will be able to answer questions during the Q&A. Also, just to note that links to the tools that Gwen and our other presenters mentioned will be posted in the chat box during the presentation. We'll also be including these links on the Climate Services webpage after the webinar, and we'll provide them by email to all attendees as well. So if you have difficulty saving from the chat box, rest assured you will have other ways to access these links. So with that, let's start Gwen's presentation.
Good afternoon, everyone. My name is Gwen Chen. I'm a research scientist at NOAA Climate Prediction Center. Today, I'm going to talk about some new tools we created at CPC to support flash drought monitoring and prediction. As you may know, drought can develop suddenly and result in major agriculture losses if it's not detected and predicted in a timely manner. This type of drought with rapid intensification is termed as flash drought. Flash drought has distinct characteristics from conventional, slowly evolving drought. This figure shows the occurrence frequency of flash drought events derived from the 2000 to 2020 U.S. drought monitor data. In this figure, a flash drought event is defined as a drought event with greater than or equal to 2 category degradation in a 4-week period based on USDA. In contrast to conventional drought, flash drought has preferred season and region to occur. Most events occur in the warm season and over the central and southeastern United States. To facilitate flash drought monitoring and prediction, several experimental tools were developed at CPC to enhance our capability of subseasonal drought prediction. I divided them into 2 categories, flash drought and subseasonal drought. Here, flash drought is referred to drought with rapid intensification, and subseasonal drought is referred to drought conditions evolving on subseasonal timescale, including drought improvement or deterioration. All these tools are accessible at CPC website under Products/Drought/Subseasonal. Forecasts are updated daily with various lead time from 1 to 4 days, depending on data availability. The first tool we developed is to monitor flash drought occurrence in real time. These tools use the same definition of flash drought that was used in the flash drought characteristic study we published in journal Atmosphere in 2019. This definition satisfies the 2 requirements proposed by Arkin et al. 2018. Their first requirement is to account for the rapid intensification rate, that is, the flash part. And the second requires that the condition must actually fall into drought during the rapid development period, that is, the drought part. This definition also meets CPC's requirement and consistent with how drought is defined operationally. On the right is an example of the flash drought monitor issued on June 1st this year. During May, there were rapid drought development over the East Coast with 2 category degradation from May 4 to June 1st. The second tool is the Potential Flash Drought Development Tool. This tool is designed to predict areas vulnerable to flash drought development, using NL-2 daily evapotranspiration and precipitation data. The Rapid Change Index is used as the drought susceptibility matrix. RCI is the accumulated magnitude of moisture stress change occurring over multiple weeks, and drought is likely to develop when RCI is negative. Because RCI, like all drought variables, change with time, so it is difficult to capture drought developing signal by just monitoring RCI map. Therefore, we count the number of occurrences that RCI is less than -0.5 over the last 30 days and plot the count map with selected thresholds specifying SPI conditions. The prediction is made by assuming that antecedent conditions will persist into the next 30 days. For more information about the methodology of the flash drought tool and its real-time verification, please refer to our paper published in journal Atmosphere in 2020. The figure on the right shows an example of the real-time prediction issued on May 19 this year. On the map, the darker the color, the more likely drought to develop. In this case, the flash drought tool indicated potential drought development over Virginia and the Carolinas, which was verified by the flash drought monitor 2 weeks later, shown in the previous slide. In this figure, you may notice that some areas with color shading did not develop flash drought, such as California, Northern Plains, and around the Great Lakes region, as this area was already in drought at the time the prediction was issued. However, there was no new drought developed in Florida, Georgia, and Alabama, as rainfall occurred in this area and prevented drought development. False alarms such like this was also noticed in our 2020 paper in the verification of the 2018 and 2019 prediction. This slide shows the predicted coverage of new drought development area from the flash drought tool and the monthly drought outlook, comparing with those identified from the U.S. Drought Monitor. The left-hand side shows the time series from 2013 to 2020, and the right-hand side shows the box and whisker plot from the time series of 89 months. In general, the flash drought tool predicts more new drought development area than USDM, consistent with the observation from the real-time verification. The current flash drought tool only uses NL-2 monitoring data, and the prediction is made under the assumption of persistent. Therefore, it highlights areas susceptible to flash drought development if antecedent condition persists into the next month. Predictions that meet the assumption usually verify well. However, drought development over area with a more variable pattern in precipitation and temperature is generally delayed or erased and not verified. Therefore, forecast information need to be considered when looking at the flash drought prediction. In contrast to the flash drought tool, monthly drought outlook predicts less drought development area than USDM, suggesting that forecasters tend to be more conservative in predicting new drought development. In May 2017, a flash drought suddenly appeared in the northern plain, caused by anomaly high temperature and evaporation in the region. CPC's April monthly drought outlook and seasonal drought outlook didn't forecast this event, and the inability to predict this event was the motivation to create the flash drought development tool. To see if the tool can predict this event, we applied the tool to reforecast the 2017 northern plain drought. The upper left panel shows the potential development issued on June 30, 2017. Comparing to the monthly drought outlook released on the same date, the flash drought tool not only captured the fuller intensification of the northern plain drought, but also 3 small areas with drought development over the northern Idaho, central Utah, and southern Texas. Throughout the 2017 warm season, the flash drought tool successfully predicted the onset and evolution of the northern plain flash drought, and demonstrate better performance than monthly drought outlook. Please refer to our 2020 paper for more detailed analysis of this flash drought and its forecast verification. In order to understand the prediction scale of the flash drought tool, I generated retrospective prediction using NL-2 historical data. This slide shows the Hikey skill score of the flash drought prediction from 2000 to 2020, verified with USDM. The Hikey skill score on a weekly basis is not particularly high, especially during cold season. This is due to the fact that evapotranspiration activity are mostly dormant and limited to southern United States in cold season. The false alarm mentioned in the previous slide also affect the skill score, but good scores are observed during some major flash drought events, such as the 2007 Southeast drought, 2011 Texas drought, 2012 Central Great Plains drought, and the 2017 Northern Plains flash drought. Here is an example of the verification for the 2007 Southeast flash drought. The flash drought prediction valid through May 15, shown on the upper left, indicated potential development over the Southeast region. This prediction was well verified with the USDN drought class change map on the upper right for the same period, and the Hikey skill score is 0.424. This slide shows another example of the verification for the 2012 Central Great Plains flash drought. This drought is a historical event and has been studied by many due to its rapid onset and significant agricultural damage. CPC's seasonal drought outlook did not forecast the rapid onset of this flash drought, which was the motivation to inaugurate the monthly drought outlook in 2013. In contrast, the flash drought reforecast valid from July 17 to August 14 show very strong development signal over the central United States and verify well with USDN drought class change map for the same period. This example demonstrates the added value of the flash drought tool in predicting fast developing drought. The third tool I will talk about is a subseasonal forecast system to provide 3 months and 6 months SPI forecasts for week 1 to 4. This system uses the same methodology as the seasonal MME SPI forecast system we developed at CPC in 2012, but based on CFSV2 45-day precipitation forecast and update daily with 32 member ensemble forecasts. On the right is an example of 3-month SPI forecast initialized on July 5th. In the figure, the left column shows the 3-month SPI forecast for weeks 1 to 4, and the right column shows the difference from the initial condition, so it is easier to identify area with increased dryness or wetness. In this case, 3-month SPI forecast indicated that dryness over most of the U.S. is likely to improve in the next 4 weeks. The fourth tool is a subseasonal hydrocarbon forecast system. This system uses CFSV2 45-day precipitation, temperature, and wind forecasts to drive the variable infiltration capacity land surface model to derive offline soil moisture, evapotranspiration, and runoff forecasts using NL-2 as initial condition. This methodology is proven to provide more skillful soil moisture and runoff forecasts than original CFSV2 and ESP forecasts. For detail of the methodology and seasonal soil moisture forecast evaluation, please refer to our paper Moore et al., published in Geophysical Research Letter in 2012. From this forecast system, I generate the soil moisture percentile forecast for week 1 to 4. The figure on the right-hand side shows an example of SMP forecast initialized on June 5th. The system used 1999 to 2020 hindcast for bias correction, and forecasts are updated daily with 16-member ensemble forecasts. In the SMP forecast figure, I also provide the drought class change forecast map for week 1 to 4. These maps are similar to the USDN drought class change map produced by the National Drought Mitigation Center, but are forecast for the future. The maps are based on week 1 to 4 SMP forecasts and assign a drought class at each grid point using USDN classification scheme. For example, a grid point with SMP forecast below 2% is assigned a D4 category. Then the difference of number of categories from the initial condition are calculated for each grid point. This forecast map can help forecasters easily identify area with drought development or improvement for the next 4 weeks. In this case, rapid drought deterioration is forecast over the upper Midwest and Northern Plains in 2 weeks. From the same hydrocarbon forecast system, I also produced the week 1 to 4 evapotranspiration and runoff anomaly forecasts, as well as their difference from initial conditions. These forecasts can be further used to create rapid change index and standardized runoff index forecasts to enhance the flash drought tool or predicting hydrological drought. The last tool I will talk about is an integrated product that combines information from the flash drought tool and the subseasonal 3-month SPI and soil moisture percentile forecast. This tool uses the latest USDM as initialization and synthesize information through a decision tree process to determine drought tendency category for the upcoming months. The forecast map uses the same format as the drought outlook map, so it is intuitive for the forecaster. By using this integration process, the false alarm in the flash drought tool can be reduced. On the right is an example of the objective drought tendency forecast issued on April 30 this year. Please note that this experimental tool currently only incorporates shortened drought indicator, and therefore the forecasts are only valid for shortened drought. Cautions are needed for areas under long-term drought, such as the Northern Plain and Southwest. Limited by time, I only provide an introduction of these experimental tools in this presentation. If you have any question or suggestion for the tools, please feel free to send me an email. My email address is listed on the slide. Thank you.
Great, thank you very much, Gwen. That's a great presentation. I'm sure people will have a number of questions. And if you do have any questions for Gwen, go ahead and put them in the questions box. We'll get to them at the end. So next we will hear from Brad Pugh, who's also with NOAA's Climate Prediction Center. He'll be presenting on an upcoming CPC flash drought product. So Brad, go ahead.
Right, well, yeah, thanks for the invitation here to show another one of CPC's flash drought tools that have been in the making here for the past year, to kind of go along with many of the tools that Gwen just went through in her presentation. Next slide, please. So just a little background on the history of drought outlooks at the Climate Prediction Center. The seasonal drought outlook began 20 years ago alongside the U.S. Drought Monitor. The intent is to present a simple national picture of where droughts will end, improve, persist, or develop. And we continue to issue a seasonal drought outlook each month, third Thursday of the month. And as Gwen noted in her presentation, following a rapidly developing drought in 2012, a year later, we began a monthly drought outlook, which is released at the last day of the month. And the major goal of the monthly drought outlook is to forecast rapidly developing and high impact droughts known as flash drought. Next slide, please. So for our monthly drought outlook, we start with the latest D1 or moderate drought areas on the U.S. Drought Monitor. And a couple of the tools we use are climatology on the monthly time scale and also the 1 month temperature and precipitation forecast to get a forecast here for the entire month. Next slide. Now, when we consider flash drought, especially during the first couple of weeks of the month, initial conditions play a major role, also weekly temperature and precipitation forecast, along with Gwen's tools that she just went through. And you can see here, this is the forecast for this month that was released at the end of August, which showed areas of development across the southern plains. So that did verify quite well using this methodology that I just mentioned, initial conditions and weekly TMP forecast. Next slide, please. Here's another example from a year ago, valid for June 2020. Released at the end of May, that correctly forecast a flash drought that occurred over the southern plains. So at the end of May, we were forecasting large area of development over the southern plains, western central Oklahoma, also the Texas Panhandle. Next slide, please. So the next two slides just kind of show the expansion of the drought from late May through the early part of June. So you see back on May 26, drought coverage was fairly limited in scale and also intensity. And just 2 weeks later, a large expansion of the D1 moderate drought and also an intensification of the drought categories over west central Oklahoma and the Oklahoma Panhandle. Next slide. And similar to Oklahoma, Texas also had an expansion of moderate drought or an intensification of ongoing drought in that 2-week time period. So overall, yeah, pretty good forecast of rapidly developing or intensifying drought over the southern plains during that early part of June. Next slide, please. So motivation here for this flash drought tool, which I'll be showing a couple slides, was to apply the methodology used for development forecast in the monthly drought outlook to our week 2 hazards product to help identify areas of flash drought when conditions warrant. Second point real important here, I think, is to take advantage of a skillful temperature forecast in the next 1 to 2 weeks. Improve communication of flash drought risk later in the month. And the reason we're including the flash drought potential in our week 2 hazards is it's become like a major vehicle to support decision support services. We have a daily briefing, headquarters briefing twice a week, and we also email to regions when necessary, depending on the climate conditions. And we also received feedback from stakeholders for several years to include this on our week 2 hazards product. Next slide, please. So inputs to the flash drought tool include initial conditions, abnormal dryness in the current U.S. drought monitor, also soil moisture conditions below the 30th percentile. As far as forecasts go for week 1, we use NDFD, positive temperature anomalies, and 7-day negative precipitation anomalies from the Weather Prediction Center. Then you move into that week 2 time scale, and we use CPC's temperature and precipitation outlooks at the week 2 time scale. Next slide, please. And just a final bullet there is kind of using this more simplified methodology. I think does have somewhat of a communication advantage for forecasters and the public to see, what's kind of driving the flash drought. Next slide, please. So yeah, I think I just have 1 or 2 more. So this is just an example back at the beginning of July. The blue shading is depicting areas where that flash drought tool was showing an increased potential for flash drought, which included the Central Plains, also parts of Northwest Montana. Next slide. So if you compare the end of June to 2 weeks later, July 13th in the U.S. Drought Monitor, the drought did expand over parts of Nebraska, intensified over Minnesota, also developed or expanded over western Montana and parts of Washington State. And didn't include it here, but the results from going back to like late August into the beginning of September also showed good results for the flash drought situation that's ongoing across the southern plains this month. And next slide. So yeah, here's an example of our week 2 hazards product. So this is not included just yet. We are planning to launch this for the next growing season. A little bit of a delay this year, but yeah, we do hope to include this on our week 2 hazards product for next growing season. So this is just an example of what the depiction would look like on the map. So it'd be kind of more broad scale, showing the targeted area that most likely could see a flash drought developing over the next 2-week period. And next slide, I think that's it. Yep. So yeah, thanks for your attention. If you have any questions, feel free to email me, Brad, or Adam. Those are the 2 email addresses there. So yeah, thanks again.
Great, thank you very much, Brad. And we put a link to where that tool will be. I believe, Brad, you had said to me it's where the tool will be in the chat box, so people at least have a heads up of where it'll come. And so now let's go to our last presentation by Trent Ford from the University of Illinois, Urbana-Champaign, who will provide a survey of everything else, so to speak, some part of everything else, some of the non-CPC tools being developed for flash drought. So Trent, go ahead.
Yeah, thanks, Marina. Go ahead and go to the next slide, please. All right, so title slide here, some emerging tools. We heard from Brad and Gwen about some at CPC that are either experimental or operational, and now we're going to go through some other ones that are broadly similar but also have some important differences. Next slide, please. Okay, so I thought this was important to start with here is sort of giving an overview of how flash drought manifests often, which sort of is necessary before thinking about what we need to monitor or possibly look at to provide some early warning or maybe even prediction to flash drought. So I'm stealing this figure here from Jason Atkins' paper in a few years ago, and you can see on the left-hand side is kind of the early signals of flash drought. We have below normal precipitation, which is absolutely necessary for any drought, let alone flash drought. But you know, the calling card of especially agricultural and ecological flash drought, where we see ag impacts and impacts the ecology, is above average demand. So that atmospheric demand, often that comes with temperatures that are above average, strong winds, low humidity, that sort of thing that's coupled with that below normal precipitation. And what that does is it quickly depletes soil moisture, especially in that rooting zone. And we can see that towards the bottom as we move out in time from those atmospheric drivers, we see a decrease in soil moisture, and kind of the namesake of flash drought means that happens rather quickly, and to the point where we begin to see deteriorating vegetation, ecological health, and that can ultimately manifest in agricultural drought or ecological drought. So when we're thinking about the timescales of monitoring and early warning, for monitoring flash drought, we're looking at things like, along with precipitation and evaporative demand, vegetation indices, maybe soil moisture. For early warning, before we see that agriculture or ecological drought set in, we really want to look a little bit earlier when we're looking at those atmospheric conditions as well as maybe soil moisture. So that gives us an idea again of what sort of indicators we really should be looking at when trying to forewarn or monitor flash droughts. Go ahead and go to the next slide, please. Okay, so some notes up front before I start going through all of these products. First of all, this overview is absolutely not exhaustive. If I missed your favorite flash drought tool, please bring that up in question and answer, and please send me a link to it in my email, because they're, you know, one of the good things about flash drought really becoming notorious in the science is that there's a lot of tools popping up for monitoring and early warning. So if I missed one, please let me know about it. Second, this is not an endorsement, an advocation, or a condemnation of any individual product or technique. We're taking these products in groups, and what I'm going to do is summarize the advantages and disadvantages of using products based off of each of these individual variables. And so again, we're not endorsing any specific product here. We're trying to provide a good summary of what we're looking at, when maybe to use certain products over others and when not to. Go ahead and go to the next slide, please. Okay, so we're going to start with evaporation and evaporative demand focused products. And so evaporation, we heard about this, Gwen talked about this a little bit in some of the products from CPC. So we have evaporation and then evaporative demand, sort of the potential evaporation, which is driven more by temperature, wind speed, humidity, so on and so forth. I have these different summaries broken up into advantages and disadvantages. Again, these are very broad. They can vary a little bit between products that use evaporation or evaporative demand, but these are sort of broad advantages and disadvantages. So some of the advantages of evaporation and evaporative demand focused products, those that use that information to produce and either monitor or early warning. Evaporative demand has been shown, study after study after study has been shown that evaporative demand, elevated evaporative demand is very important for flash drought. We need those above average temperatures. We need a lot of drying out of that soil moisture. And in a lot of cases, just below average precipitation won't create that sort of rapid onset or rapidly intensifying conditions that characterize flash droughts. So it's really important to get that high evaporative demand, and therefore evaporation, evaporative demand focused products can give us information that others may not be able to, for example, just precipitation alone. Also, a lot of these products, because of they're either drawn from atmospheric reanalysis data sets, other data sets, remote sensing data sets that have been around for a while, they often benefit from a relatively long climatology. So a lot of times I think both Brad and Gwen mentioned the anomalies, maybe percentiles kind of translated to the US Drought Monitor. Both of those often rely on a relatively long climatology to be able to capture not just the mean state of evaporative demand, but also the extremes. And when we're talking about flash drought, it's really the extremes that matter. So adequately capturing those really depends on a relatively long climatology, and a lot of these products benefit from that. Also, global scale, especially those that rely on models or remote sensing data sets, that they inherently have a global scale, which means that they don't just benefit the US or one particular region in the US, but the entire globe. And that can be really important as well, as I'll talk about in a little bit. And then they have the potential for high spatial resolution. A lot of these products are at fairly fine scales, in some cases getting close to field scale spatial resolution, which for some other products, for soil moisture namely, we may not be able to get to. Some of the disadvantages is that models are really important for this data set, but of course, when we depend on models, all models are wrong, some are useful, and so the dependency on model information can create issues in certain situations. Evaporative demand, as I mentioned, is really important for flash drought, but it is not explicitly tied to precipitation, and it has a variable connection to soil moisture. Depending on the climate that you're in, if you see changes in evaporative demand or evaporation, they could inherently be tied to soil moisture. And in some climates, especially very humid climates, that may not necessarily be the case. And so evaporative demand and evaporation-based indicators may be better predictive of or better for early monitoring of flash drought in certain climates than others. And so that nuance has to be taken into account. And then, as Gwen mentioned, I think in the HITKey skill score plots that she showed before, the variable cool season performance, because evaporative demand is not as important in the cool season as the warm season, especially in more temperate climates. We can have different variable cool season performance as far as monitoring for flash drought in the cool season. Go to the next slide, please. So some examples of evaporation and evaporative demand focused products: the evaporative demand drought index, which is one taking the figure here on the right hand side, one of the more recent EDI maps here, and the evaporative stress index is another one, and then the standardized evaporative stress ratio. Now these are all similar to each other. Some use for example, EDI is focused on evaporative demand, whereas the CSER, standardized evaporative stress ratio, takes the ratio of evaporation to evaporative demand. So how much evaporation, how close evaporation is to meeting the potential of evapotranspiration, which can give us a bit of a signal about soil moisture and moisture conditions. And so, and evaporative stress index also takes into account vegetation conditions as well. So they are varying to a varying degree, but they're all sort of getting at the same ideas: how arid is the atmosphere, and how much does that relate to how much can that drive the amount of soil moisture depletion leading up to flash drought. Okay, go ahead and go to the next slide, please. All right, so then on the other side, when we think about flash drought as an atmospheric kind of driven event, we think of the other side of evaporative demand as precipitation. The advantages of precipitation focused products is that, precipitation is a necessary component of drought. It's the same with flash drought. Precipitation products also tend to benefit from a long climatology. We've been measuring precipitation in many places around the US and globally for a long time now. National to global scale, often the spatial extent of precipitation is not usually an issue. There is potential for high spatial resolution, especially with some incorporating radar and remote sensing information. And this is important from my perspective, coming from a flash drought from the soil moisture perspective. We don't really have a lot of good forms of information for calibration and validation. It's certainly not everywhere across the US, let alone globally. For precipitation, that's not the case. There's multiple forms of information. There's assimilated model-based data sets, entirely remotely sensed, or radar-based data sets, and then you have entirely gauge-based data sets, and then you have these hybrid data sets that are a mix of all three or more. So what that gives us is a lot of information to do calibration and validation, which is, again, coming from a perspective of a data set that may not have that benefit, can be really advantageous. And then we've been studying precipitation and its effect on drought for a long time now, a century or more. And so the legacy of that knowledge fits into how well we can anticipate impacts based on precipitation-based indicators. The disadvantage of precipitation is that, kind of on the flip side of the disadvantage of evaporative demand, precipitation is not tied to evaporative demand. So even if we have below normal precipitation, if it's cooler, if it's more humid, we may not have the evaporative demand, we may not get a flash drought in some regions. Precipitation is highly variable as far as the quality and quantity by country, which means it's not necessarily very consistent across political borders, which can create a problem when you think about global flash drought monitoring. And there's a timescale mismatch with precipitation. When we think about a 30-day total, or a 60-day or a 6-month total, for example, if you even if you update that once a day, it's not necessarily going to be highly predictive of when a flash drought occurs. A 30 or 60 or 90-day precipitation deficit is necessary to get flash drought, but it's not necessarily going to be predictive of when that flash drought will occur. So that's going to be really important, whereas often precipitation alone is not a great monitor of flash drought, but it can be combined in tandem with something else to make a good product. Go ahead and go to the next slide, please. I guess oh, there it is. Okay, good. All right, so precipitation focused products, and to this last point that I made, one of them that I'm picking out here, the integrated water portal. Right now it's being hosted by the North Carolina State Climate Office. I should mention though that it's soon moving to the Southern Regional Climate Center, and so that'll be exciting to see that there in its new home. One of their products they have is a daily updated SPEI, that's Standardized Precipitation Evapotranspiration Index. And so, kind of to my last point from the previous slide where I was mentioning coupling precipitation with another indicator like evaporative demand, that's what gives us the SPEI, which can better monitor more rapid changes in evaporative demand on top of precipitation deficits that lead to flash drought. We also have really important ACIS SPI maps, or Standardized Precipitation Index maps, from the High Plains Regional Climate Center, among others. And then the global SPEI drought monitor, which is also a really important indicator, again, using that Standardized Precipitation Evapotranspiration Index, but at a global scale for global flash drought monitoring. Okay, go ahead and go to the next slide, please. All right, I guess the second to last group of products are soil moisture focused products. The advantages of soil moisture is that it's arguably where the rubber meets the road. Soil moisture is indicative of agricultural and ecological impacts in many areas. We begin to see those agricultural and ecological impacts when soil moisture reaches the point, whether it be the wilting point or some other point at which plants are no longer able to meet that water demand. And it integrates, soil moisture integrates the effects of precipitation and evaporative demand. So it kind of combines the two together. Soil moisture products, there's the potential for national to global extent for scale, and it tends to have a low false positive rate. We tend to not get a lot of false positive drought warnings when our soil moisture is low. When we have very dry soils, we tend to see those drought impacts pretty consistently, which is important. The disadvantages of soil moisture is that we have a really highly variable and lacking in most places in situ monitoring infrastructure for soil moisture. What that means is we're relying a lot on models of remote sensing, and I'll see this sometimes in the literature where we're validating a soil moisture model with another soil moisture model, and it's just because we don't have that in situ monitoring infrastructure in many places that's dense enough to really do a lot of work with that information. There's a variable climatology of soil moisture. In some places we have 20 to 30 years of information, but in most places, especially with station-based soil moisture, it's often very short. That goes the same with a lot of our remote sensing products too, where like SMAP, for example, which has been up in the sky for 6 years now. It's good. That data set is important, but the relatively short climatology makes it a bit challenging to convert to, again, we're talking anomalies or percentiles. The spatial variability and representativeness is always a problem with soil moisture, and using one point to represent a whole field, let alone a whole county, let alone half a state, is really complex. And then there's communication complexities. Even with current soil moisture monitoring data sets and tools that are available, I see a lot that there'll be a product put out and it's a percentile, or it's a volumetric water content, or it's an anomaly. And for folks who aren't working day to day with soil moisture, it can be really difficult to translate that to, okay, how much water do I either need to apply to my crop, or how much water is my soil lacking in the root zone? And so communication with soil moisture is a bit trickier than it is with something like precipitation. Go to the next slide, please. Some up and coming, so soil moisture based flash drought monitoring has been lacking other types of data like evaporative demand and precipitation, and for good reasons. All the complexities that I just talked about with soil moisture, but there are some up and coming products. I think Brad and Gwen hit on some with CPC. I also wanted to highlight the Flash product, Flash Drought Assessment using SMAP hydrology, which is based the Vadosone group there at Texas A&M. I showed an image here of recent, and this is using SMAP information at a global extent to try to indicate where there may be areas that are going into flash drought or coming out of flash drought. And it's a really novel tool that I think has good front end development. So that's one to check out as well. And then there's some work by a few groups, and I know CPC hit on this a little bit, but there's some work in a few groups that are trying to couple soil moisture conditions, either current or near term predicted soil moisture, with subseasonal seasonal forecasts of meteorology. So trying to get at, okay, here's where our soil conditions are at now, and then here's where our atmospheric conditions look to go in the next couple of weeks, 2 to 4 weeks, maybe farther out. And that gives us a bit of an early warning for areas that may be going into flash drought. Not areas that are in drought, as Gwen kind of highlighted. Those areas are not really what we want to look at for flash drought. It's the areas that have the potential in the next few weeks to go into flash drought. So that's something to look at as well. And there's a great paper by David Lorenz and the Wisconsin group there that was just published a few days ago. Go ahead and go to the next slide, please. Okay, last bit here, integrated products, and I wanted to touch on these. These are taking a bunch of different information. It's not just soil moisture, just precipitation, or just vegetation indices, but a lot of things put together. Some advantages, of course, you can, when you take in a bunch of different data points, you can leverage the advantages of those individual variables. So it kind of maybe removes some of the disadvantages of the individual products. You have the potential to depict nonlinear relationships, which we know exist between precipitation, evaporative demand, soil moisture, and it can maybe provide a confluence of evidence that can perhaps result in a more stable result. The disadvantages of integrated products is that it may not respond as quickly as other drought products. We see that with the U.S. Drought Monitor. It's updated weekly and takes into account many longer term indicators that may not be as relevant for flash drought. And the communication interpretation is complex as well. We're not just saying, okay, here's how much precipitation, here's how much rain you're going to get next week. It's here's how this was depicted based off a machine learning algorithm or something like that. It may just make communication and interpretation a bit trickier with these. Go ahead and go to the next slide, please. Some integrated products example, of course, we have the U.S. Drought Monitor, which is that confluence of evidence sort of approach at trying to get at drought monitoring. QuickDry does this. QuickDry uses a number of different information, but to its credit, it does update rather quickly, hence the name. And so it is actually a useful tool for flash drought monitoring. And then Beth Hall at now at the MRCC and at the Indiana State Climate Office has built a flash drought risk tool using machine learning, and they're working on that right now, and it's combining a bunch of variables together, and it has a lot of promise. So I wanted to highlight that as well. Okay, go to the next slide. Final thoughts. Thank God, I'm done. A couple things. There is no single best flash drought indicator or product. I don't think there ever will be. Much like drought, it depends on the situation. It depends on where you are. It depends on who you're talking to. Are you talking to agriculture folks? Are you talking to natural resource managers? Are you talking to municipal water managers, for example? There's different, often complementary information from products, and so using them again in tandem really produces the best results. And then there are some aspects that do seem to be consistent among successful products. For example, focus on the onset intensification and the rate of change more than traditional drought indicators. So a lot of times when we think about traditional drought indicators, it's how much rain have we had over the last 3 months, right? That doesn't really give us an idea about flash drought, which is really about the potential of intensification. How bad is it going to get in the next couple of weeks? And so looking at the rate of change can be really important. Gwen hit on the rapid change index, which is really, I just wanted to highlight that again. That's shown a lot of promise to be applied to multiple different types of indicators to really reflect that rapid change. And then again, the inclusion of some sort of evaporative demand, because flash drought is so important the evaporative demand part is so important, it's really important to include. Last, current needs, as far as I've seen them here, as we think about the next 5 years of flash drought monitoring and tool production, and this list here is in order in my opinion of priority. I think the first thing is a stakeholder empowered flash drought product. So if we create 30 new flash drought products in the next year, but none of those are actually linked to what stakeholders actually need as far as information, that may not be as helpful as if we create 3 or 4 really good products that have stakeholder input from the beginning to the end. And then in lieu of time issues, I'll skip the list of the other current needs, but yeah, hopefully this was helpful, and I want to thank again the organizers here for letting me spill my thoughts here.
Well, thank you very much, Trent. Sorry to have you stop. That was a very, very rich presentation, but I do think it would be important to have some time for question and answers. I just want to say real quickly, I know we posted a number of links from the presentations in the chat box, and we will be including those links on the Climate Services webpage after the webinar, and we'll be sure to email them to you as well. So don't worry about trying to cut and paste all of that. So again, thank you everybody for the great presentations. We've reached the Q&A part of the webinar, and I'd like to invite the panelists to turn their cameras on, and then we'll turn to my colleague Maggie Hurwitz to moderate this section. Maggie?
Thank you, Marina, and thank you to all of the speakers for your great presentations and all you're doing to advance this field. So first, Trent just addressed sort of the future of flash drought monitoring, but I wanted to turn to Brad and Gwen in terms of what you see as the future of flash drought predictability. Sort of what are the limits of predictability, and how can we get there to kind of the next generation of tools? So Brad or Gwen, any thoughts?
Yes, I think I want to apologize first. It looks like my camera is not working, so you cannot see me. But yeah, to answer Maggie's question about flash drought predictability, I think we have some ongoing research that was doing at the CPC that was led by the Hailan Wang, and she's looking to, to use like the subseasonal hindcast and looking at precipitation and temperature from subseasonal model to evaluate those forecast field and their predictability. On my side, I'm mainly working on developing tools and verify their, for prediction scale. So I don't know if Brad have any thought on that.
I think, yeah, Gwen touched on everything there. Yeah, I think the difficulty, and Trent talked about this, is just the monitoring aspect of it, the soil moisture networks around the country. And then in terms of predictability, skill and precipitation is always a tough challenge. I guess the upside for flash drought is you're looking at a shorter term precipitation forecast. So you're looking at the next 1 to 2, 3 weeks. So perhaps a little bit better skill in that time range than when you're looking at more of a seasonal precipitation forecast.
Yes, I agree.
Go ahead, Gwen.
Yeah, I just agree with what Brad said. I think for flash drought tool, based on what I see from the, the current flash drought tool, we see the scale, it's for the next 2 weeks, we have, very good confidence on that, on those prediction. But going out to like week 3 and 4, because the precipitation forecast scale at week 3 and 4, generally is lower and then the week 1 or 2. So, so the scale decreases, and as we go to the seasonal time scale, then, then it is a very challenge to predict flash drought on the seasonal time scale. Yeah, that's all I have.
Okay, thank you again. So there was another question about basically defining flash drought, and I think most of you approach flash drought as a rapid development of drought, but do you also look at situations where a drought is getting more severe, where there are areas of existing drought, or other definitions?
Yes, I
Yeah.
think the current flash drought tool, it actually can apply to area that already have drought, because we do see some area, that's already in drought, but the flash drought tool, still showing signal for further intensification. So, I didn't, because for our monthly drought outlook, we mainly want to predict the drought development for new drought development. So I didn't, particular looking at the drought that's already, intensify in the already drought area. So yeah, but that's a very interesting question to look into.
Yeah, real quick, Maggie, I think a good point is that this is why it's important to look at the rapid change, the change and not necessarily the absolute value. And so if an area is already in drought, but they're expected to not receive much, if at all, rain and high temperatures, then they could see an intensification. And that's where the same kind of tool that can maybe provide some early warning or monitoring of onset could also do the same for intensification, sort of as Gwen mentioned.
Thanks. So another question was about whether we need to have different metrics for flash drought for the Western US, and I would also say for the global products for other arid regions like Australia, for with irrigated agriculture and arid landscapes, the flash drought would be different from, for example, from the Midwest.
I think so. I would say the majority of flash drought work so far has been done related to agriculture and in either humid or semi-arid environments. There has been some work in arid environments, but I think that's something important to flesh out in a research way is what indicators tend to work better in which climates and at what time scales, and that'll really, I think, give us a better idea of what to use where. Similar to what's used in the U.S. Drought Monitor, where, for example, as we move into winter, snowpack may be more important in the West than whereas soil moisture is important in the East and Midwest.
Megan, I'm just going to jump in, Marina, here, just to say we are at the top of the hour. I'm hoping the panelists can stay on just a little bit longer. Obviously, others may well have to leave. We did get many questions, though, that we won't have a chance to get to, but we have documented all those, and we will follow up with that email with all those links and some additional questions. But again, maybe we can keep going just a little bit longer on questions here, Maggie, if you're available.
Yes, sorry, I just lost my audio connection, but I think I'm back for now. So one other question that piqued my interest was about latency and, you know, the need for timely information given that the time scales of flash drought. So, for example, this questioner talked about eddy, and it's 5 days old when produced. Can you comment on that and what we can look forward to going into the future in terms of reducing this latency?
Yeah, I'll take first shot at that. So I didn't put specific advantages or disadvantages of any product, but one of the big disadvantages from eddy is its 5-day lag time or latency. And when looking at, and of course, eddy is not specifically a flash drought product. It can be used for many other purposes, including traditional drought, where it may be less important for the latency time. But yeah, I think for flash drought, more than for maybe a more traditional drought, the latency of a data product becomes more important, and especially as it relates to evaporative demand, because at least from my perspective here in the Midwest, if we have a prolonged 30 to 60 day pretty dry spell, it only takes a handful of days of very warm, dry weather to really hit that point where we see some maybe flash drought impacts. And so having a latency more than just a few days can make the difference between representing that, maybe providing some early warning, it could be effective and not. So when thinking about tool development, I think data latency should be really important along with other factors when developing those tools.
Yeah, I think Trent answered that very well. I don't have anything to add.
Maggie, are you still there? We can't hear you if you're speaking. Oops, we might have lost Maggie's audio there. Okay, well, with that, I think, unless Maggie, you can hop back on here, as Marina said, we have captured all the questions. So if you did not get your question answered, we will definitely follow up with you. We wanted to thank you all for attending today's webinar. When you close the webinar, a survey will pop up, and we ask you just to take a moment to answer the brief questions, if you don't mind, to give us some feedback on the webinar. But another thank you again to all of the speakers. We really appreciate you, the effort you put into today's webinar, and thank you everyone for joining.
Hey, thank you too. I just want to say that if you have any question like we couldn't answer, during the webinar, and then, please feel free to send me to me by my email. And then I think I can, answer better, through email. Thank you.
Thank you so much, everyone.